Hello and welcome back to this online short course by Red Door Analytics, Survival Analysis, an Introduction to Concepts, Methods and Software. In this part of the course, we're going to go through the software tutorial in Stata. So I've opened here the questions that you should have received or have access to, where we are going to look at analysing a data set containing 115,000 breast cancer patients diagnosed between 1986 and 1999 in England and Wales. The thing that we're interested in is estimating all-cause survival of these patients since the breast cancer diagnosis, where we'll focus on variables age and deprivation status at diagnosis as confounders of this association. So things that are important to note are that we have this deprivation status, which may not be so well known to everyone. This is defined by something called the Quintell-Carstairs score. But really what you need to know is that we have indicator variables for different categories of deprivation called DEP1 to DEP5, with the least deprived individuals being in DEP1 and the most deprived being in DEP5. And we also have an age group variable, which is age group 1 to age group 5. We can look at this when we go through the data ourselves to see what this looks like. Okay, so you should be able to see on the left-hand side of my screen the results window in Stata, where all the results are going to come out soon. And then on the right-hand side, you should be able to see the tutorial.do do file that you should have access to, so we can run through this together and look at the results together. So what we're going to do first is just read in the data set. So you can see here we use the use command, and Stata tells us that the England and Wales breast cancer survival data has now been read in. So part one looks at no modelling. And the first question just says, get familiar with the data set. So we have the describe variable here, or command here. So we can look at what variables are in our data set. We can see that we have 115,000 observations with 21 variables. We see a little bit more about the data set, some descriptions here. And then we have lots of different variables included in the data set, some information about the storage type and variable labels, which are important here, so we can understand what we have in our data set. So I think the most important variables for this analysis are that we have an identifier, an ID variable for each individual. We have a sex variable, so if they're males or females. We have this Carstairs score, which is the deprivation status, but we will always use the variables called DEP1 to DEP5 in the analysis. So this is a categorized version of that DEP variable. So the important things to know here is that DEP1 is the least deprived individuals and DEP5 are the most deprived individuals. Then we have information on region, which we won't be using. We have the date of diagnosis of their breast cancer. We have, what else is important here? The age at diagnosis in years. We have a dead variable, which tells us whether these individuals died or not. So this is 1 when they did die and 0 otherwise. Serve time, it tells us the follow-up time in years. So we will be using that. There's also a date exit, which gives us the date of exit. So we can use serve time to look at follow-up time, or we could use the date diag and the date exit. And the other variable that is of importance here is age group, or the indicator variables for each of the age groups for age group 1 to 5. And we'll look at that a little bit more later. So let's just look a little bit more at the deprivation status here. As I said before, we've got 5 different groups in this deprivation status, where 1 is the least deprived and 5 is the most deprived. And we can see that this is somewhat equally distributed across our observations with no missing information, which is important. We can also look at the serve time variable, which tells us how much survival time we have in our data set. And we can see that we have follow-up from 0, which makes sense because we're looking at time since breast cancer diagnosis. We have a maximum follow-up of around 10 years. serve time is in years. So the second question tells us to look at the first 15 individuals in the data set with respect to the variables which are relevant for this tutorial. And what we start by doing is formatting the date variables, because otherwise we will look at, if I run the list command here in our do file first, you will see that we have date diag here and date exit, and these are not interpretable for us. This is just Stata's way of recording date. So if we format first these using this command and then list them again, we should be able to see something that's more interpretable. So what we do see is we have different identifiers here. And I don't think this is sorted on the identifier. So what we can do is we could sort by ident and then rerun this if we wanted to. Oh no, here we are. It's the same. Or it looks very much the same. So what we can see is that we have different ID variables here representing different individuals. We have a deprivation status for those from 1 to 5. This is the categorical variable, but we've also got indicator variables for each of these. So if you land in deprivation group 2, we have a variable dep2, which is equal to 1 for those individuals. We have a date of diagnosis for the breast cancer patients and their age at diagnosis. You can see here that those individuals presented in this specific 15 are very old. And based on that, we can see that the survival time is very short. If we look at serve time here, this is in years. So we can see that they are all under 2 years here, except for this person who survived 5 years. And we can see that they all died at the end of their follow-up time here. And we have a date of exit, which is equal to the date of diagnosis plus the survival time here. And then we have age group variable here. So we can see that they all are in the eldest age groups. We may also want to look at the age group variable, and we can do that by doing this. And we don't get much information here. We can see that we have 5 different groups. We don't really know what age they are within each of these groups. So what we can do instead is we can use the command by sort age group and then summarize the age at diagnosis. What is the variable here? Age diag. So we can look and say, okay, within age group 1, we say by sort age group. So it spits out the summary at each of the values in the age group. We can see that in age group 1, we have individuals diagnosed from age 17 to 50. In age group 2, we have 50 to 59-year-olds. Age group 3, we have 60 to 69-year-olds. Age group 4, we have 70 to 79-year-olds, and age group 5, 80 plus. So the next question here, number 3, says use the SDSet command to tell Stata that we have time to event data, and remember that we're interested in estimating time from breast cancer diagnosis to death. And this is all-cause death, so no specific cause of death, just any death. So what we can do is we can use the variable serve time, and the failure indicator dead is equal to 1. So we tell Stata we want to follow across serve time, and we want you to know that the failure event is when dead is equal to 1. So we can run that and we can look at what we get in output here. So we have our command repeated here and then the output from SDSet, where we can see some replication of what we entered here at the top. We see that we have this amount of individuals in our data set, and we can see that we have 58,000 failures, which means we have 58,000 deaths in our data set. And this corresponds to 575,000 person time at risk. So this is person years at risk in our data set. And again, we can see that we follow from 0, that's time of breast cancer diagnosis, until around 10 years, where our last observed exit is. Note that in the do file, I've also specified that you can write this out differently using SDSet. You can use the date variables instead. So we can say that instead of following serve time, which is a bit easier in this context, but if you don't have serve time in in your own analysis data sets. You can use the date of exit. So we say we want to follow to date of exit. We have the same failure here. But we say that you enter the study at the date of diagnosis. And this happens to be the same as the origin of the timescale. So the date of diagnosis is when our timescale is equal to 0. That's what that means. And then we tell Stata that we want to scale this down to years. And we have an ID variable here just for later on. So if we run this, we get exactly the same output. There may be some rounding differences, but otherwise it's the same. So let's just use our serve time instead, because that's a little bit easier. And let's look at what is created when we run SDSet. So when we run SDSet, what happens in the background is that Stata creates some variables. So you should be able to see those in your data set. And here I've listed what they are: _st, _d, _t, _t naught. So these variables are created in the background so that Stata can use them for any subsequent ST commands, survival analysis commands. So anything that we run later that starts with ST, these are all going to use this information that's created in these 4 variables. Now, it may be easier for us to understand this a little bit better if I rearrange these a little bit. I'm just going to change this here so it's a bit more intuitive. Let's go like this and rerun this just so we can have a look. So what we can see here for these first 15 individuals, and now we've got different individuals than what I had presented before because I have done some sorting on age group when we looked at age. So it doesn't matter, we have different ages now, so that's probably quite nice. So we can see that the first individual were followed for 9.9 years, at which point they were alive and censored. So we can see what the _t naught is here. For everyone, this is 0 because we follow everyone at time point 0 at time of diagnosis of breast cancer. But you can see that _t is our follow-up time. So this is the same as serve time here because we follow from time 0 until _t, the time of exit. _d gives us our event indicator, which here is the same as the variable dead. So this is 0 for alive or censoring. And the _st variable tells Stata, do we want to include this observation in any subsequent survival analysis? In this situation that we have here, every value will be 1. There will be situations where you don't want to include everyone in survival analysis. And so you would get 0s there, and then any subsequent commands would not include those observations. But for now, we have all of these will be 1 for everyone in the data set. So if we just look at the second person here, we can see that they had a survival time to 4.55 years, and we follow them from our Stata created data sets. We can see 0 to 4.55 years, at which point they died, and we see that that's mirrored in our _d variable, which is equal to 1. So the next part of the question is use the SDS graph command to plot the Kaplan-Meier cohort curve for the entire cohort with the number of risk. And we can use the graph to estimate the median survival. So let's have a look at what the command does here. We can run this and get a Kaplan-Meier curve out. So basically the SDS graph curve command gives us the Kaplan-Meier curve. We've just added some options here so it looks a bit nicer. We've named this so that we don't overwrite our graphs when we start producing more graphs. We've added an X title and a Y title. And the risk table option gives us the number at risk. So here you can see that we have the probability of survival here on the Y-axis. And on the X-axis, we have the time since breast cancer diagnosis in years, which goes up to about 10 years, as we saw previously. And we can see how the number of risk of individuals decreases across the time scale. So if we're interested in estimating the median survival, what we do is we look at, okay, the median survival is when it's equal to 0.5. So we can go across the curve, across the graph, and say, okay, is 0.5 at around this point, which is just over 7 years. So that would be our estimate from the curve. But what we can do is we can use the STCI command instead to get the actual value, so we don't have to estimate this. So if we do that, and I just close this, we can see that at 50% survival, so the median survival is at 7.13 years. And we have a standard error associated with that, so we can calculate a confidence interval as well. So now we're going to go and look at our deprivation status here. So if we're interested in looking at the Kaplan-Meier by deprivation status, what we can do is add this by dep. So let's do that and have a look what we get. So we can see this output here, where we have 5 different curves. Otherwise, it's the same Kaplan-Meier curve. It's just split the cohort into 5 different groups defined by deprivation status. And you can see at the bottom, we have a legend representing the least to the most deprived. And you should be able to see that those that have the highest survival are those that are the least deprived, and those that have the lowest survival across the timescale are those with the most deprived. Not particularly surprising, but good to see the pattern across the deprivation groups. So the next question says, look at the SCS graph command with the hazard option to get a general idea of the shape of the hazard function, and note that these should not be overinterpreted. So what do you conclude from this? So let's have a look at that. So we'll start by looking at the graph overall. And we can see that the hazard seems to decrease over time. So this is the hazard of death across our time scale. There's some little dips and troughs here at the beginning and the end, and we shouldn't overinterpret anything like this, because this is maybe a not so great smoothed line of the hazard function. And then if we look by deprivation status, we can see here again that we see this decreasing trend over time, where we now see on the hazard scale the flipped association by deprivation status, that those that are the most deprived generally have the highest hazard function across time, and this decreases across the deprivation group. So the least deprived have the lowest hazard, which isn't surprising. So question 9 tells us to use the SD rate command to calculate the crude mortality rate in the entire cohort per 100 person years. So let's do that. We use the SD rate command and we use the option per 100. And we get this output here. So D tells us how many events we have across our timescale. And if you remember, this is the same number that we had in the output from SDSat. Y tells us our person years at risk, and this is per 100 person years. And then we have a rate, which tells us that we have a rate of a mortality rate of 10 per 100 person years, alongside a lower and upper confidence interval. So we are asked about the total person time at risk and the number of deaths in the cohort. We've discussed that. And then compare this to the output from SDSet. We can do that by looking at just typing SDSet again, and it will re-output the SDSet that's in the saved memory. And we can see here that we have the same number of events and the same person time at risk, or person years at risk. If we want to then go on to question 10, where we want to calculate the crude mortality rate by deprivation status, we can do that by using the same command, but we add the variable dep here. And then we can see the number of events within each of these, the person time at risk, and then the rate.